Okay, this lecture is going to be dealing with a sense of scale of the universe. First thing we're going to be doing is comparing the sizes of the actual planets and celestial bodies that you're going to find in space. Second thing is we're going to basically look at the distances in space. And then the last thing is we're going to focus on the concept of light and look back time and the speed of objects in space. Okay, so what this is actually called is this is called the cosmic distance scale. Okay, so whenever you start looking at scales of the universe, you have to understand that space is actually really, really big. It's mind-boggling how big space can actually be. But you saw where we were in our galaxy in the last presentation. Well, now just imagine we're going beyond that. And we're starting to look at just the vastness of space. So, what are some of the things that I want you to focus on knowing? Well, first thing I want you to do is I want you to be able to compare the size of the actual planets. This is a video that basically kind of gave us a scale going from the quantum up until extremely large things. So you guys have already watched that, so I'm not going to waste time there. So here's a comparison of the inner and outer planets. The thing that I want you to focus on here is not that this is not a comparison of distance. This is a comparison of size. So you can see there approximately 11 Earths would fit across the surface of Jupiter. So that looks how big that is. Saturn is very close in size, but not quite. Jupiter is, of course, our largest planet. You can also see that Venus is very near the same size as Earth. That is why it's actually referred to as Earth's twin, is because it has a very similar size. And then, of course, Uranus and Neptune. Most people think that these planets are actually large gas giants equivalent to Jupiter and Saturn, but you can see they are significantly smaller. And they're more accurately referred to as ice giants. We'll be looking at why they're called ice giants in Chapter 6, and you'll have a better understanding of that. Okay, here's some comparisons right here. You can see here's a size comparison of the inner planets. You can see, of course, that Venus, as I mentioned before, Venus and Earth are very similar in size. Mercury there is on the bottom right, and of course Mars is at the bottom left. Here you can see a comparison of the outer planets as compared to the inner planets. Okay, you can see they are vastly, vastly different in size. So please know your actual sizes of the planets. Kind of like if you look at Venus, if you look at Jupiter being about the size of a basketball, then that would put Earth approximately at the size of maybe a ping pong ball or something like that. So be able to make those comparisons when looking at the actual sizes of these objects. Now, here's where it starts to get very interesting, because if you start to look at the size of the sun and say the size of the sun were a basketball, then you're looking at the size of Earth being about the size of a pea. Okay, 99% of the mass of the solar system is right there within the sun. So you can see that it is vastly greater in size than the planets. And this is typical among stars and planets themselves. There's a great difference. And you'll understand later why they're so different in size. Here you can see, this is just a really cool picture. I like always doing comparisons of sizes of planets to stars and other objects. Of course, we're going to use the Earth pretty much always. But just imagine something like a solar flare coming off of the sun. Now you can see why we're so concerned about these things, because they could literally engulf the actual planet. So, and that's pretty significant. What you're seeing there is actually what is called a solar prominence. You can see that it's kind of arching right through there, and Earth would actually fit into that prominence. So, really neat kind of picture there. It's one of my favorites. Okay, as I mentioned, you can see about 11 Earths can fit across the size of Jupiter. You can get almost, this picture's a little deceiving because you can almost get about 2 Earths inside of what is called the Great Red Spot, which is a gigantic cyclonic storm, very equivalent to a hurricane here on Earth. Then you can look at North America. You can get about 5 to 6 North Americas in there. into the Great Red Spot. And the Great Red Spot, as you saw in the previous slide, is not, it's big, but it doesn't, take up much of the surface. And then you start looking at Saturn and how we would fit into the ring system. And this is the one that's really interesting to me because most people think of comets and they think that they're like small celestial bodies. Well, here you can see what a comet looks like, a typical comet looks like in comparison to something like the city of Los Angeles. So these things, whenever they come by, there are smaller ones, but typically, a lot of people have a misconception of just how big comets actually are. Now, whenever you start comparing the size of the sun, you can see that, wow, our sun is actually very small compared to someone like Betelgeuse, which is, one of the larger red stars. It's found in the upper arm. So if you're looking at Orion, it's that upper right arm, the big bright red star. That is Betelgeuse. Rigel would be the lower foot of this constellation Orion. So you can see our sun in comparison to those stars doesn't really, ours is actually a small star. Okay, next thing we want to focus on is now distance. Whenever you start talking about distance, of course, we have units in astronomy that are very unique. We're back to that cosmic distance ladder. These are things that we use to measure distances in space because, of course, we can't take a tape measure and just say, hey, let's go there. Can't use an odometer in a car. So we're going to talk about how do astronomers actually find distances later in the course. What I want you to know right now is that we have three basic units of distance. The first one is what is called the astronomical unit, or the AU. This is the average distance from the sun to the earth. So whenever we say 1 AU, that means that that planetary body is either 150 million kilometers or 93 million miles away from the star that it's actually orbiting. Okay, so that's the first one. The astronomical unit is typically used for planets and planets only. We do not use the unit of AU with stars because they are much farther away. What you can see here is this is kind of a scale of, I will tell you that Mercury and Venus are missing from this, but Mercury is at about right in this area. And then Venus, that's at about 0.24. And Venus is at about 0.72. So it's about right in this area, okay, where my pointer is at. So you can see that the planets are actually quite spaced out. It doesn't give you kind of the vastness of it on this diagram, but they really are spaced out significantly because you look at Mars is, it's 0.52 AU away. So 0.52 times 93 million miles, you're still talking about, a good significant, you're talking about 49 million miles. That's why it takes 6 months to actually get to Mars from Earth. Okay. And then you get, of course, out here to Jupiter. Jupiter is at about 5.4 astronomical units. Then you continue and you'll notice that the spacing of the outer planets becomes much greater. But then you can actually see that we can get all the way out here to where it's what is called the Oort cloud. That's 10,000 astronomical units, and it extends all the way out to 100,000. So what this does is give you a kind of a vastness of just our solar system. Our solar system is just absolutely huge. To kind of give you an example, we launched our probe in 1976, the Viking probe, and just last year, I believe it was last year or maybe the year before, it's right in this time frame, right around that time frame, that it actually just went beyond Pluto. Okay, here's kind of a distance to scale between the Earth and the Moon, so it doesn't look too far, but what's really unique is you can actually fit all of the planets within that distance. I found this amazing whenever I first learned this. I was like, whoa, if you put all the planets side by side, you can fit every planet in our solar system in between that actual distance. So the moon is actually quite far away. One moon journey takes, 3 days? I believe is what it is. It takes 3 days to actually get to the actual moon. Okay. Whenever you start looking up at the night sky, I will tell you this is very, very interesting to say that whenever you see the stars that are in the night sky, The stars that are most predominant and that we can see with the naked eye are all within that yellow circle. So that just gives you a sense of the vastness of space. There are stars out there that the light hasn't even reached us yet, which I found just absolutely amazing. Okay, here you can kind of see just some more scale. This is the size of a Milky Way. It's about 100,000 light years, wide. Okay, the next unit is, of course, the light year. We're going to go ahead and use 300,000 kilometers per second. So anytime you do any types of calculations, please just go ahead and round that up to 300,000 kilometers per second. Here's the thing. A light year is the distance that light travels in 1 year. Okay, most people inaccurately use light year because they use it like a sense of time. It is actually it's actually a distance. Okay, it has nothing to do with time. It's just the distance that light can travel in 1 year. The thing that I want you to kind of know about it, though, is it is kind of our cosmic speed limit. Nothing can exceed the speed of light within our solar system. So light is considered to be the fastest. Now, there's some new research out we'll talk about later, so we're not going to jump ahead of ourselves. But for right now, just go on. The fastest thing is actually the speed of light. And a light year is a distance. Now, here's the thing that you have to remember, and this is what's really cool, is every time you look into the night sky, you're seeing everything as it was in the past. Even the sunlight from our star, the sun, you're seeing 8-minute-old light, okay? Because it takes 8 minutes for us to reach. So as soon as that light leaves the surface, it actually takes 8 minutes to get to the surface of Earth before our eyes can actually see it. So every time you start hearing about the term light year, that's really how long it actually takes for the light to reach us. Okay, so an extremely large number. Again, you saw on the previous slide, it's like 6 trillion miles, excuse me. Well, it's really, let's not go there. What astronomers are trying to do is they're trying to reduce the size of numbers because they can be so large. A perfect example is like we don't say that, we're 475,000 feet to Branson. We basically say that we're so many miles away from Branson. So this is the same concept. Okay, so please understand whenever you start looking at that, you are looking at something that is called look back time. So in other words, this is kind of really neat, and I always like to discuss this. If we were to look at the star Sirius, and Sirius were to explode right now, okay? So Sirius has a distance of 8.61 light years away from us. Well, because of that, it can explode right now, and we would not explode until we wouldn't know that it exploded until 8 years from this moment. So it's very interesting to understand that concept of look back time. Okay, so of course, the more distance that an object is, if we look at something that is 10 million light years away, we're looking at light that left that object 10 million years ago. Okay, so what we want to do is we want to look at some of the most distant light. And of course, some of the most distant light that you think we could see is 13.7 billion years old, but that's actually not true. And we'll cover that a little bit later as well. It's not that big of a concept right now. Okay, next thing you want to look at is the next unit, which is called the parsec. This is very difficult to understand right now. We'll be covering this a little bit later. Please just know that the parsec is 3.26 light years away. Okay, and what this parsec is it's a new unit of distance, but how you obtain this unit of distance is quite a challenge right now. Whenever we get to stars, we'll go over more of this. So just understand right now and be able to convert light years to parsecs and parsecs to light years, etc., etc. So 1 parsec is equal to 3.26 light years. Okay, this is what it is. It's parallax shift. So what you do, I always do this of saying, okay, close one eye, open, close this eye and look at your thumb, and then switch eyes. Well, you notice that your thumb appears to shift. Well, that's the unit, and that's how they obtain this parsec. Okay, they look for that apparent shift of a star, and from that we can use geometry to determine the distance. So don't worry about doing this just yet. We'll come to this later in the course whenever we get to the stars unit on how to measure distances. Okay. All right. And then, of course, there is one more unit called the megaparsec. We're not going to worry too much about that. All right. So what you can see is that for every distance, we tend to use different units of measurement. If you're talking about our solar system, you're going to use the astronomical unit. If you're talking about stars, we're going to start to use light years. But then as soon as you start to get that number up again to where you have like hundreds of millions of light years, we can actually switch over to the parsec and even the megaparsec, which you're not responsible for. But that's what we're going to be looking at doing. So just know those actual sizes of that. Okay. Last but not least is how fast. Now this is one thing that I want you to remember. Speed of light. Speed of light is 300,000 kilometers per second, 186,000 miles per second. So what you could do is you're going to be able to use that number to, make calculations and determine how long it takes light to get from one object to another. What you're basically looking at here is light has a constant speed, does not change no matter what the medium it travels through. So that is something to always remember. Speed of light is constant, always 300,000 kilometers per second. Okay, here's the other thing I want you to know, that no matter what form of energy, be it radio, microwave, infrared, UV, X-rays, visible light, gamma rays, they all travel at 300,000 kilometers per second. So every time you send a text message, 300,000 kilometers per second. Every time I turn on a microwave, that energy is traveling at 300,000 kilometers per second. You turn on the radio, 300,000 kilometers per second. So that's a key thing to remember. A lot of people look at this and say, wow, the wavelength there, because that wavelength is much shorter, that's the distance between the two peaks, that's called the wavelength. The frequency is how many of those things pass a given point. So of course this is high frequency, this is low frequency. Most people think that the speed of anything on the electromagnetic spectrum is dependent upon either the wavelength or the frequency. Please realize it is not. Okay? Basically, this is one of my favorite things to do.
Han Solo. I'm captain of the Millennium Falcon. Chewie here tells me you're looking for passage to the Alderaan system.
Yes, indeed. If it's a fast ship.
Fast ship? You've never heard of the Millennium Falcon?
Should I have?
It's a ship that made the Kessel run in less than 12 parsecs.
Well, of course, what's wrong with that statement? He used parsecs as a unit of time. Okay? Parsec is a unit of distance. So, that concludes this portion of the review. Primary things to focus on is, of course, focus on how big, know the scales of things and kind of be able to make simple comparisons. Second thing is to know how far, so know your units of measurement. And then third things, please know that the electromagnetic spectrum and that all forms of energy travel at 300,000 kilometers per second. Okay, our next lecture video is going to be focusing on the observations of the night sky. That's going to be a big one.